Hello, everyone. Welcome. Thanks for joining us today for another one of our Roth IAMS webinars. We're just going to give it a couple more minutes as people are joining, and then we'll get started. So again, welcome everyone to another one of our Roth IAMS webinars. Today we have one focused on our structural services practice. So we're going to get started now. Just a few housekeeping notes to share. As usual, following the webinar, we will send out an email to everyone with a copy of a link to the deck and to the webinar playback as well. Throughout the webinar, we will have some poll questions, so we do hope you'll participate. It gives us a bit of insight as to what you're all working with and will help us as we develop more webinars. Additionally, at the end of the webinar, before you leave, we would ask that you take our survey. That's at the end of the webinar. As I said, that helps us organize webinars that meet your needs and gives us a bit of insight as to what you're all dealing with. So we're going to get started now. And I am going to turn the meeting over to Andre Cullen, our service lead for our structural practice. Today, our webinar is about the building envelope, the science of protecting your building's environment, and the art of layering. Over to you, Andre.
Thanks, Amanda.
Sorry, Andre, I'm going to jump back in. Apologies, everyone. I forgot to mention the chat. We will have room for Q&A at the end, so if you do have questions, please put them in the chat and we will address them at the end in the Q&A section. Sorry about that. Continue, Andre.
Thanks, Amanda. So our agenda for the webinar is I'll do an introduction after. I'll just go through the agenda here. So the agenda for the webinar is understanding building environmental flow and control, the fundamentals of effective layering, system weak points and diagnostic tools, and then we'll touch on some of the advancements in instruction methods and envelope materials. And then we'll look at a case study and some key lessons in protecting your building envelope. And we'll end with some question and answers. So my name is Andre Cullen. I'm the practice leader for structural engineering for Roth IAMS. I'm a professional structural engineer with 25 plus years of experience and knowledge in structural design, evaluation analysis, and forensics and restoration of existing structures, as well as new design in steel, concrete, wood, and masonry. My experience is managing structural condition assessments and forensics for facilities and infrastructure assets such as stadiums, post-tension parking garages, and retaining walls, as well as historic structures. I'm responsible for the Roth IAMS structural team, which is 7 engineers across North America, and we provide efficient, cost-effective phase 1, phase 2 structural condition assessments and analysis, as well as capital repair plans and repair recommendations. So, and I just wanted to say, I am fighting a bit of a cold, just getting over it. So I apologize in advance if I do cough. I'll try not to. It's been pretty good this morning, so hopefully, fingers crossed. So, understanding building environmental flow and control. Shelter is a basic human right. It's recognized internationally in documents like the 1948 Universal Declaration of Human Rights and the International Covenant on Economic, Social, and Cultural Rights. To protect and maintain the longevity of our shelters, we need a building envelope, which separates and protects the outside of the building from the inside. Most early buildings, cladding systems are either brick or siding. Brick masonry is very porous, and siding systems have a lot of gaps and movements, so they were not perfect. Older wall systems had large air gaps, which were great for dealing with issues for locations for water drainage and breathability to help with keeping wall systems dry. But these were very drafty and not very energy efficient. Heating a building with such big open air gaps were very expensive and extremely energy inefficient. So it's a contradiction. While we need this separation for survival, we complicate things as humans because we want to still have a connection to our outside environment, to bring the outside to the inside. We could solve all our shelter and envelope issues by simply living in a cave like early humans, but we've come a long way for the ability to protect our family and ourselves within our buildings, yet enjoy the benefits of sunlight and fresh air for our health. This is the science and art of building envelope. The main purpose when we think of a building envelope layer is often thought of in energy terms to act as a thermal barrier. There are several different flows or environmental movements which the envelope barrier protects us from. Our knowledge and understanding from science has accelerated at a very fast rate to predict and design protective membranes around our buildings. The environmental conditions we need to protect against are heat, liquid water, water vapor, and air movement. Firstly, perhaps the most damaging is water. Water can rot the envelope, and if not caught or detected early, can continue behind the envelope and cause hidden damage to the structure below. Water flows governed by gravity or capillary action flows from higher to lower elevations. As often described, water will find the quickest path and easiest path of least resistance to the ground. For comfort, we also minimize and protect from wind and air flowing from the outside to the inside of the building. Large air gaps can create very drafty and uncomfortable spaces for inhabitants. Air movement flows from higher pressure to lower pressure. The biggest comfort in our buildings and the largest impact on energy usage and loss comes from heat flow. The thermal barrier in our wall system keeps us warm in colder climates, as well as keeps us cool in hotter climates. So heat always flows from hot to cold. The trickiest flow throughout our wall system, and one that is not as often thought about by us as inhabitants, is water vapor. Water vapor flows become an issue when vapor condenses and forms water. Water vapor always flows from higher concentrations to lower concentrations. So thinking about these flows and movements through the elements helps us to better understand the makeup and layering necessities of a building envelope system. So let's look at these flows a little closer. We want to prevent rain from entering and accumulating. It's pretty straightforward. We can achieve this through a strong water control layer. Water is the most damaging to the structure and can cause wood rot, corrosion, and health consequences such as mold growth when it enters into a wall or roof system. If it doesn't have a way to dry out, it can be very, very damaging. Warm air holds more moisture than cold air. So for example, a glass with ice. In a room with high enough humidity, the warm moist air gets cold and forms water droplets on the outside of the glass. The air can no longer contain that amount of moisture. This is the dew point of the air. Similarly, in cold climates, the inside air tends to be more humid as air leaves the inside of the building to the outside. It gets cold and condensation can occur. So a vapor control layer, vapor barrier, is needed inside the wall, inside the insulation, thermal layer cavity, to prevent condensation on the wall system and elements. The control of airflow is a crucial and intrinsic part of heat and moisture control in building enclosures. A large fraction of a modern well-insulated building space conditioning energy load is due to uncontrolled air leakage. Wintertime condensation of water vapor in exfiltration air or summertime condensation of infiltration air within assemblies is one of the two major sources of moisture in the above-grade envelope system. Driving rain is the other. Airflow through the enclosure can also carry exhaust gases, odors, and sounds through enclosures, as well as mold, spores, and off-gassing generated within the enclosure. Uncontrolled air leakage through the enclosure is therefore often a major cause of performance problems, comfort, health, energy, durability. So the primary reasons of why the control of airflow is important to building performance is number one, for moisture control. Water vapor in the air can be deposited within the envelope by condensation and cause serious health, durability, and performance problems. Secondly, it's for energy savings. Air leaking out of the building must be replaced with outdoor air, which requires energy to condition it. Approximately 30 to 50% of space conditioning energy consumption in many well-insulated buildings is due to air leakage through the building enclosure. And finally, it's for comfort and health. Cold drafts and the excessively dry wintertime air that results from excessive air leakage directly affect human comfort. Wind-cooled portions of the interior of the enclosure promote condensation, which supports biological growth, which in turn affects indoor air quality. Whoops, I'm sorry. I clicked too far here. I apologize. So airborne sound transmission control also requires good airflow control, and odors and gases from outside and adjoining buildings often annoy or cause health problems. So temperature changes from season to season have a significant impact on a building's energy use and occupant comfort. This makes the concept of thermal control an essential part of the design process, with the goal of having a more thermally efficient building. Understanding heat transfer and how certain building materials can be used to impede it is the first step in meeting this objective. Incoming and outgoing heat flow is a prominent factor in determining a building's comfort level and operating cost. Heat has a natural tendency to flow from an area of high temperature to one of lower temperature. The greater the temperature difference, the more the heat flows through an assembly. For example, a heated building will lose heat to its colder exterior in the winter, and during the summer, an air-conditioned building will draw heat from its very warm exterior. The rate of heat transfer through the wall depends on two things: the temperature difference between the interior and exterior, and the makeup of the wall materials. Some materials such as glass, concrete, and all metals transfer heat very well and are called conductors. Other materials such as fiberglass and foam sheathing are referred to as insulators with a high resistance to heat flow. There are three different ways through which heat transfers in and out of a building. Conduction is probably the best known and easiest to understand heat transfer mode. It takes place when a material separates an area of high temperature from an area of low temperature, such as a wall. Convection, the second most common heat transfer mode, occurs as a result of liquid or gas moving over a surface, such as wind blowing against a building. There are two types of convection: forced and natural. Natural convection occurs when the movement of liquid or gas is caused by density differences, and in forced convection, the movement of the liquid or gas is caused by outside forces. Radiation involves the transfer of invisible electromagnetic heat waves from one object of higher temperature, such as the sun, to another of lower temperature, such as a human body. So to make a building more energy efficient and comfortable, building and design professionals need to impede these modes of heat transfer. Though it is impossible to stop these processes entirely, it is possible to significantly slow them down by placing obstacles in their path. This is referred to as breaking the thermal bridging. So now we'll take a poll question. So what signs, disruptions do you feel in your building's environmental flows? There's a bunch there, and choose all that apply. So we have some answers coming in. Looks like we've got about 30% leaks and water buildup and 30% uncomfortable, too hot or too cold. And drafts are coming up as well. Great. Whoopsie, sorry. So, fundamentals of effective layering. The order of the control layers is very important. Simply keep the structure on the inside and it will stay dry. As a reminder, the 4 control layers are the water, rain control layer, the air control layer, the vapor control layer, and the thermal control layer. A leaky building is an immediate problem. Over time, it can rot the structure. Buildings with drafts are very uncomfortable. Water vapor should not accumulate inside the building envelope walls. This can lead to mold, rot, and worse, hidden structural damage. For energy, we need insulation, needed to reduce energy flows. So first we need a wall that is structurally sound, a wall that does not get wet. Once these immediate concerns are dealt with, to eliminate that threat to the structure itself, we can concentrate on dealing with the levels of comfort in dealing with draftiness and energy efficiency. So let's look at the layers a little closer. The exterior cladding is the outermost layer. While it gives protection, it cannot act as the vapor control or water control layer. Its main functions are to protect the building from damage and to act as the building's design feature. Common modern-day cladding types are metal, stone cladding, vinyl, glass, composite systems, and brick. Air barriers are crucial for controlling air infiltration and exfiltration, which can lead to drafts, heat loss, and reduced energy efficiency. Common air barrier materials include house wrap, a synthetic vapor permeable membrane wrapped around the building to create a continuous barrier. Sheathing, rigid panels made from materials like plywood, oriented strand board OSB, or rigid foam, which can serve as both structural support and an air barrier. Sealants, caulks, tapes, and gaskets that seal joints, seams, and penetrations to prevent air leakage. A successful air barrier system should be continuous, airtight, and durable. To achieve this, it is essential to carefully design and detail the air barrier, ensuring that all potential leakage points are properly sealed. Proper installation by trained professionals is also crucial for long-term performance. Weather barriers protect the building envelope from water penetration, wind, and UV radiation. Some common weather barrier materials are house wrap. House wraps can serve both as air and weather barriers, providing a continuous vapor permeable layer around the building, depending on the climate for which they are installed. There's also building paper and asphalt saturated felt or craft paper that provides a breathable moisture barrier. Liquid applied barriers. These coatings form a seamless monolithic layer that resists water penetration and air leakage while allowing vapor transmission. The choice of weather barrier material depends on the specific building requirements and local climate conditions. Factors to consider include moisture exposure, temperature fluctuations, and wind loads. Selecting the appropriate weather barrier material and ensuring its proper installation for long-lasting protection and durability is crucial. This may involve overlapping seams, sealing penetrations, and integrating the weather barrier with other building envelope components, such as flashings and window openings. Proper insulation is the foundation of an energy-efficient building envelope. Various insulation materials are available, each with distinct properties and applications. Such common types include fiberglass. Lightweight and easy to install, fiberglass is a cost-effective option that provides good thermal resistance. Mineral wool, made from rock or slag fibers. Mineral wool offers excellent fire resistance and soundproofing qualities. Spray foam. This versatile insulation expands to fill gaps and cracks, creating an effective air and vapor barrier. Rigid foam. Typically made from polystyrene or polyurethane, the rigid foam provides high R values and is often used for exterior sheathing or continuous insulation. The effectiveness of insulation is measured by its thermal resistance or R value. Higher R values indicate greater insulating power. To select the appropriate insulation for specific climate and building requirements, consider local temperature extremes, humidity levels, and energy code requirements. Vapor barriers. Vapor barriers control moisture migration through the building envelope, preventing condensation and mold growth. Common vapor barrier materials include polyethylene sheathing, a durable and cost-effective option, typically used in walls and floors. Vapor retarding paint, specialized coatings that provide a moisture-resistant layer on interior surfaces. Foil-faced insulation, rigid foam or batt insulation with an aluminum foil facing that acts as a vapor barrier. The optimal placement of vapor barriers depends on the building's climate and construction type. In colder climates, vapor barriers are typically installed on the interior side of the insulation, while in warmer, humid climates, they may be placed on the exterior side. It is important to consult local building codes and best practices for guidance on vapor barrier placement. The anticipated vapor condition and building codes determine whether you will need a vapor impermeable and a vapor permeable air barrier. However, the complicated nature of this decision often requires a building engineer to decide the best air barrier for your product. So let's look at cold climate control layers, such as an example in northern Canada. The difference in water transmission rate brought about by use of barrier material for vapor diffusion is substantial. Condensation forms within insulation layers when hot, humid air contacts a cool, dry surface. In the diagram on the left, the warm air in the building could create condensation within the fiberglass insulation, depending on the R value and dew point. So a better design on the right shows warm, conditioned air is kept inside the building without collecting in the insulation, and vapor from the outside can enter and exit the assembly through the permeable membrane. In hot, humid climates, like in Florida, materials in a wall makeup will be different. An incorrectly used vapor barrier on the outside of the wall could cause potential issues and damage to the structure. In the diagram on the left, the moisture permeates the air barrier, then collects on the concrete wall where it cannot dry out due to the high humidity. On the right, the optimal placement is when an impermeable vapor barrier, waterproof weather membrane, will be more successfully on the outside of the control layers. In keeping out water vapor, that has a hard time drying in humid climates. So let's look at another poll question. So what are the most concerning deficiencies you see in your building's envelope cladding system? Again, choose all that apply. So they're just coming in. A lot of thermal breaks, but now it looks like it's getting spread around to cracked sealants, failed roofing membranes. Quite a bit actually on all of them, spread all around. So weak points and diagnostic tools. The building envelope, which includes the roof, walls, windows, and foundation, serves as the first line of defense against the elements. Variable climate with cold, snowy winters, hot, humid summers, and plenty of rainfall, along with a compromised building envelope, can quickly lead to serious issues. Catching building envelope problems early is key to minimizing damage and repair costs. So what should you look for? Water stains or leaks. One of the most obvious signs of potential building envelope issues is the appearance of water stains on walls, ceilings, or around windows and doors. Repeated freeze-thaw cycles in winter can cause particular problems with melting snow and ice finding its way into small cracks and openings. Cold water on a flat roof is another warning sign that drainage issues may be putting strain on the building envelope. What starts as a small stain or occasional drip can signal the beginning of a much larger problem. So never ignore water where it shouldn't be. Another thing to look for is cracks in the facade. While small hairline cracks in stucco, brick, or stone may not be cause for major concern, Large cracks, especially those that appear suddenly, could point to a building envelope problem. A shifting foundation damage from freeze-thaw cycles or moisture getting in and breaking down materials can also cause noticeable cracks to form. So keep an eye out for cracks larger than 1/8 of an inch wide, horizontal cracks, which can signal serious structural issues, and those that seem to be growing rapidly. Another thing to look for is bulging or bowing walls or structural members that are bulging, bowing, or pulling away from the building are a major red flag that warrants immediate investigation. This could be due to water infiltration breaking down the wall assembly materials, hydrostatic pressure form, saturated soil, or foundation settlement issues, among other causes. If you notice any pronounced inward or outward displacement of a wall, contact a building envelope and structural engineer right away to diagnose the issue and recommend a repair plan. Waiting will likely only lead to more severe and costly problems. Another thing to look for is a spike in energy bills. So a more subtle sign that your building envelope may be compromised is an unexpected increase in heating or cooling costs. Hot, humid summers put air conditioning systems to work, while the cold winters means cranking up the heat. If your HVAC system seems to be working overtime compared to previous years, it could be due to air leaks or insufficient insulation, letting that conditioned air escape. While many factors can influence energy bills, it's worth taking a closer look at your building envelope if you suspect it may be the culprit. An energy audit can help identify areas where your building may be leaking air. So you also want to look for mold or mildew growth. Finally, the appearance of mold or mildew inside the building is almost always a sign that moisture is getting in where it shouldn't. While mold can be a serious indoor air quality issue on its own, it's also a symptom of an underlying building envelope problem that needs to be addressed. Mold thrives in damp environments, so its presence signals that water is infiltrating the building somewhere, likely through gaps or leaks in the envelope. A mold remediation specialist can help clean up the immediate mold issue, but you'll want to bring in building envelope experts to correct the water intrusion problem itself. And always remember, always contact a professional expert to determine the underlying cause and appropriate repairs. The earlier, the better. Finding weak spots and failures in the building envelope control layers is key in maintaining the remaining useful life of buildings and ensuring there will be no expensive damage or deterioration to the building structure. There are a number of key technologies and methods which can be used to assess and to help. So thermal imaging, thermography, uses infrared technology to create a heat map of the building, making it possible to identify areas of heat loss, poor insulation, and moisture that are not visible to the naked eye. There's also blower door tests, where a large fan is mounted in a doorway to pressurize or depressurize the building, which helps to identify leaks in the building's air barrier. Pressurized spray racks. These racks use a high volume of water to simulate heavy rainfall on exterior components like windows, walls, and cladding to test for water penetration. Ultrasonic leak detection uses sound transmitters to detect small gaps, often in combination with other methods like spray testing. This can be a non-destructive and efficient way to locate air leaks. Then there's also air tightness and water tightness testing equipment. This includes specialized test chambers, sensors, and software to quantify air infiltration and water leakage rates under controlled conditions, often based on standards from organizations like the ASTM. What they are used for: air leakage, identifying and sealing gaps that allow uncontrolled airflow; water intrusion, finding vulnerabilities in the building's exterior where water can penetrate; thermal performance, evaluating insulation and identifying areas of heat loss or thermal bridges to improve energy efficiency; and quality assurance, verifying that the building's construction meets design specs and industry standards. So now we'll look at some of the advancements in building envelope materials and construction methods. So new advancements in building envelope technology and innovations are focusing on enhancing energy efficiency, sustainability, and occupant comfort by enabling buildings to better adapt to environmental conditions. Some of the latest advancements include smart materials. So smart materials that change properties in response to their environment. Some of the examples are thermochromic glass that tints based on sunlight, and phase change materials that absorb and release heat to regulate indoor temperatures or advance. Other advancements include dynamic facades, so facades that adapt to changing conditions. This includes systems with automated shading, responsive materials, and kinetic elements to optimize energy and comfort, and adaptive solar panels, building integrated photovoltaic systems that have moving parts to track the sun or adjust their orientation for better energy capture. Construction materials and assembly methods are also advancing for optimization of the building envelope control layers. Some of these include modular construction, so prefabricating building envelope components off-site to increase precision, speeds up construction, and reduces waste. Advanced insulation, developing new insulating materials to significantly improve thermal performance and reduce heat loss. And there's also hybrid sealant technologies like new sealants made from modified urethane acrylic that are durable, low VOC, and designed to create a better system with building wraps. So we have another poll question. Have you used any testing methods or technology and assessing your building envelope, and choose all that apply? It looks like thermal imaging is one that's a common one that's used. That's one that's commonly used for existing buildings. But a number of other tests were also used. It's great. So now we'll look at a building envelope case study and some of the lessons that were learned. So the building we'll be looking at is an 11-story concrete, steel and concrete masonry block structure constructed in 1966. The total structure is approximately 13,702 square meters in area, located in a cold northern climate. The building is constructed with a steel reinforced cast-in-place concrete frame supported by drilled concrete piles and grade beams. The upper floors and roof consist of precast concrete double T joists supported by the concrete frame. The envelope consists of storefront systems, concrete masonry units, and brick veneer at the ground level, with the remaining floors clad in a precast concrete panel system with integrated insulated glazing units. As plans for the building were not available, details concerning vapor retarders and air barriers could not be confirmed. In 2006, an engineering study was completed, which was at the 40-year life of the building and its components. Consultants identified multiple issues concerning the building envelope and recommended performing a number of repairs. In their report, they also provided an explanation of the risks of not proceeding with the recommended repairs. So recommendation number 1 was recaulking replacement on various building elevations to maintain the integrity of the face-sealed building envelope system. A remaining useful life of 3 years was given for the original caulking. The risk of not proceeding with that repair was water can penetrate behind the panels at failed locations, allowing potential for deterioration of building envelope substrate and anchorage systems. Recommendation number 2 was an annual allowance to replace sealed glazing units and perimeter window gaskets and caulking. So a remaining useful life of 5 years was given for the original window glazing units. Risk of not proceeding with those repairs is failed units will have significantly lower thermal resistance, and failed gaskets and caulking allows increased air leakage rates. There will be potential for condensation and mold to form, as well as water to penetrate. So the continuation in the study, there was a third recommendation was to repair upper precast panel cracks and panel erosion repairs. The risk of not proceeding with that was structural wall panel deterioration will continue and at an accelerated rate. And recommendation 4 was building envelope and precast anchor inspections at years 5 and 10. And the risk of not proceeding with those was deficiencies will not be detected, allowing potential for accelerated deterioration of substrate and anchorage systems. So fast forwarding to the latest engineering study, which was completed in 2023. This was at the 60-year building life. And the results of the investigation assessment revealed some precast panel cracking repairs were completed, which is great. Some windows were replaced, which was good, but 60% were still original windows. Also, some caulking and gaskets were replaced, which was good, but 80% of the precast panel caulking was still original. So it's not so good. So as a result of the failed caulking and sealants in the precast wall panels and failed seals and window gaskets, thermal and airflow allowed condensation to form and water to penetrate to the inside of the wall system. The most serious issues observed are that the precast building envelope wall panel anchors are showing extensive corrosion and cracking. A very expensive repair will be needed for a large portion of the anchors. This would be a combination as part of the repair of cleaning the connection and painting with zinc-rich paint or full removal and replacement. So what are the lessons learned? Maintaining the integrity of the 4 building envelope protective layers are essential. Understanding the potential risks from the flows through the layers is key. Repairs and maintenance of the building envelope is extremely important throughout the life cycle of the building. If there are any compromises or deterioration in the envelope system, repair them quickly. And the risks are that do the repairs early, and it's a lot less expensive than major repairs that can occur down the road. So just wanted to thank you all for your attendance and attention, and here's some of the references that were used for this webinar. And now we will go to any questions that anybody has.
Thanks. Thanks for that, Andre. Yes, the Q&A is open. If you have a question, please drop it in the chat. Oh, see. Oh, what is RUL, Andre?
So RUL is remaining useful life of your building or your elements. So in all elements, when they're looked at, have a life, a useful life, which is a UL, no problem. So a useful life would be, let's say, a structure 75 years, and then so at the 60-year mark when that engineering report was done, there would have been 15 years in the structure of the building, remaining useful life of the building.
Yeah. Thanks for that question, Trina. We all deal with a lot of acronyms, and asking sometimes for clarity is important. Anyone else have any? Seeing none, I guess we can move on. Andre, would you like to share?
Yes, so just for more thought leadership, please scan the QR code and you can go to more of our sessions and thought leadership articles that we have on our website.
Yes, yeah. To answer that last question, we will be sending out an email to all those who registered with links to copies of the presentation, both as a hard deck and as a playback video. So yes, you'll get a follow-up email with both those links.
Great. So thank you all for attending again, and you can contact us directly. Here's my email. You can contact me directly, phone number, and if you have any questions, additional questions, or structural envelope questions, please feel free to contact me.
And please do fill out the survey before you jump off. Thank you, everyone, and we'll